So one of the things I like to do actually is start at exactly 59 seconds into the first minute of the talk. That way, everyone can be late but still be on time. And usually when I say this, someone walks in at just the last minute and it's awkward, but this time someone's leaving. Bye, it's all cool, don't worry. So my name is Guy Royse, and this is my talk, Finding Your Meme Twin with Embeddings and Vector Databases. This is one of those data science-y AI kind of talks, and I always have some caveats with those. But in this particular case, there's some things that I want to kind of, there's like some points. They're not in my slides, but they're points that are important to me that I want to convey to anyone when I talk to anything about this. And the first point is that everyone thinks to do AI stuff you need to use Python. Well, maybe not everyone thinks that. You can use C#. I want to challenge that. I'm doing all of my stuff in TypeScript because that's one way to live your life. The other thing is often when you want to do a lot of these new AI-enabled apps, it involves using some sort of cloud service. I am not using a cloud service. Everything is running on my 5-year-old Intel Silicon MacBook today. Yeah, so if it runs on my machine, it sure as hell is going to run on your machine. This thing's old enough, my battery lasts about an hour. So, and the third thing that I like to convey is that there's often the idea that you use some cloud service, you're going to put down a credit card, and you're going to have to spend money. Well, this is running locally. I'm not spending a dime. So I'm using Hugging Face Transformers. It's all running locally. Technically, I use the internet to download the model the first time that I run, and then after that, it's cached. But so, no cloud, no money, no Python. That's what I want to, if you walk away with only that information, know that you can do all this stuff with the language you want to use and without spending any money. So, the other thing that I kind of like to get across is the level of understanding we need to have of this technology. So I'm a developer. I should go to this slide here. Hi, I'm Guy Royse. I'm a developer advocate at Redis. I'm a developer, and for a lot of this kind of technology, we need a level of understanding akin to a mechanic who works on your car, not a mechanical engineer who designs engines. So I don't need to know in excruciating detail how all the exact details of math and everything work. People have done that, and they have built packaged things that I can use. And so as a developer, I need to understand what goes on under the hood, but I don't need to understand it at the level that I can create it myself. That said, I am going to show a way to create embedding models yourself. Not the preferred way, it's the way I know, and it's mostly to show that these things are knowable. So I like to joke that there are 3 things on this slide here that matter. One of them matters to you in the audience, one of them matters to me, and one of them matters to my boss. He would like you to know that Redis is a powerful vector database that can do all sorts of things, AI related. We're going to show that off in my demo today. The bulk of the talk is going to be just about what the heck's a vector, what the heck's an embedding, what are vector databases, what kind of problems can you solve with them, and get an intuitive mechanics understanding of these things as opposed to a deep engineer's understanding of them. So, big caveat, so that's the thing that matters about. The thing that matters to me are the social media links that are up there. So give me a follow if you're still on social media and haven't deleted it from your life, which is probably what you should do. But give me a follow. And the thing that matters to you is the GitHub link. I have code, and it is out there on GitHub for you to peruse. So if you want to try the demo out that I'm going to show off today, then that's where you go. So the other thing I always like to say is, I am not a data scientist. I have a mechanics understanding. I do not have an engineer's understanding of what's going on here. And so I'm not a data scientist. I go out and I learn about these things and I get an intuitive understanding with them and I share them with audiences. And that's what I'm doing today here. So if you're looking for like deep data science knowledge, I'm not your man. I'm not your guy. Get it? Because my name's Guy. It's the joke. So, but I'm not a data scientist, and so what I'm going to say is going to be true enough at a level of accuracy that we can work with. And there's probably some data scientist out there that says, well, actually, and I don't care. So just out of curiosity, actually, is anyone here a data scientist now that I've made fun of data scientists? Anyone? One? So what you should do is actually listen to everything I have to say and ignore the data scientists in the room. So I've got 4 agenda items for my talk today. Is 4 agenda items a lot? Well, depends on the context. For a talk at a conference? Absolutely not. It's perfect. For a talk with your boss? These items are, what the heck is an embedding? We'll talk about what these things are, how to make them, what you can use them for, how to make those embeddings, and I'm going to go into details on convolutional neural networks specifically. This is an older way of making embeddings, but it's the one that I know. And the goal there is to sort of share that it's knowable, but not necessarily to get a deep understanding of how to make embedding models yourself. I do have a talk where I talk about how to build your own convolutional neural networks that I think I did it here several years ago. It's called Deep Learning Like a Viking. And then I've got some code to show you, all in TypeScript, and a demo where we will find out who my meme twin is. And if we have any volunteers from the audience, we may find out who your meme twins are as well. So if anyone wants to come on stage and be embarrassed, then you're welcome to. So we'll start with what's an embedding. So a lot of these images I use in my slides, the memes are like these kind of low-res, standard definition television kind of things, and so I had to upscale them and add content in Photoshop to make them wider so they get a nice 16:9 ratio and look good on the screen here. And I love that this picture in the bowling alley from The Big Lebowski has an additional rifle barrel over here behind him. That's what all bowling alleys in America are like. The AI saw a gun, and so it said, what this picture needs? More guns. Yeah. So what is an embedding? Well, to talk about what an embedding is I want to talk about the types of data that we work with as developers and as developers who are building AI tools. There's structured data, and this is the stuff that we've been using our entire career. This is the numbers and the strings and things like more complicated things like maybe latitudes and longitudes, but they're things that you can put after a where clause in a SQL statement. Right? Software, we've known how to solve this problem for a long time. It's something that's well established. And we can do simple comparisons and ranges and get all kinds of meaning out of it. And then there's unstructured data. And unstructured data is things like text, prose, not text like a string, but text like a paragraph of information. And from that text, you might want to get the information about, does this text mention fast food restaurants? And you could do like a full text search and we'll look for the word fast and food and restaurant, but it wouldn't find McDonald's. And so this is unstructured. There's meaning in there that we can extract, we need to extract, that is easy for humans to do, but is a little more challenging for computers up till recently. Things like images. People can look at images and very easily determine whether there's a kitten in it or not. I like kittens, so let's go with kittens. But that's a harder problem to put in a where clause in a SQL statement. But AI is good at these sorts of things. And audio is a similar thing. I've actually thought it'd be fun to do a demo with an audio analysis or classification where you can give it some sound and say, is there applause in here or booing? And I think that would be a great interactive demo for an audience, because then I could have all of you boo me, and then we could have the boo meter go up, and then have all of you applaud me, and the applaud meter goes up. But these are all examples of unstructured data that you can manage with AI more effectively than you can with traditional means. And specifically, we're going to talk about how we can get embeddings out of this kind of data and what those are. We know how to use structured data. We've been using it our entire careers, arguably for our fathers' entire careers. This is kind of the default. You put it in SQLite. All of our structured data just goes in SQLite, right? That's what all the really big companies are doing. No? So it goes in Access then. How many of you worked on a project where you had an Access database that grew too big and then you had to convert it to like a Visual Basic application? Ask me how I know. Yeah. Not Access, maybe not. So maybe Excel. So structured data is a solved problem. Unstructured data is a problem that is being solved today, and in many ways is solved, but there's a lot of innovation happening. The idea here is you can take unstructured data, text or an image. Here we have a meme. Don't need to debug your code if it doesn't compile. This is why I like JavaScript more than TypeScript, because it doesn't compile, so there's no need to debug it. So you can take this text, and you can turn it into an embedding. And the way you do that is you run it through a model or a pipeline. A model is going to extract a bunch of numbers out of it. And so maybe we take this text and it's too long, and so we might need to run it through an LLM and summarize it. Or maybe we'll chunk it up if we're doing some sort of RAG application or something like that. This is clearly very short, so summarization probably isn't necessary. Then the model will tokenize it and find out the individual tokens in that phrase, and that would include things like punctuation and suffixes and prefixes. So like uncompiled would be un and compile and ed. It'd have 3 tokens in it, potentially. And then once you've got those tokens, you can run them through your model and create an embedding. And this is just, the embedding is the trained neural network, or the model is the trained neural network that knows how to do this. It takes that tokenized data and spits out a pile of numbers. This is an embedding. It's also a vector. An embedding is it's just an array. It's an array of numbers. The model has a fixed size that it spits out. So perhaps the text embedder that I've used has, I think, 384 32-bit floats that it spits out. So it represents a point in space, 384 dimensions. Images are similar. Lots of these pipelines that the tooling will build for you. We'll do a transformation to scale them down and make them square and put little black borders on them if need be. And then if you're using a convolutional neural network, you might go through a series of convolutions to identify features of the image and then get a final embedding layer. And again, you get a pile of numbers. And this pile of numbers is the embedding. This array of numbers, it is the embedding. And the thing that these numbers represent are features that the model has extracted. It is recognized. And so perhaps we have an image of Leonardo DiCaprio with a coupe glass and a cocktail. And the model may recognize certain features like the elderliness of the individual in the photo or the alcoholicness of the individual in the photo. These aren't real. Most models are going to have a lot more than two points, 2 things you could measure on. But this pile of numbers represents, in the case of the model I'll be using later, 512 features that are meaningful to that model. And we don't know that position 17 is elderly and position 24 is alcoholic and maybe position 317 is some other thing. We don't really know that, but we do know the numbers tend to be similar. And so conceptually we can think about this in 2 dimensions and look at 2 simple traits. And so we get a score. And in this case I'm using -1 to +1. 0 to 1 is also a common option. And so in this case, Leonardo DiCaprio isn't particularly elderly, but he's not exactly young, and so it's just slightly below 0. That's his ranking. That's the AI has looked at this picture and said, it is kind of low on the elderly side, but not like young. But he's got a cocktail, so clearly it's alcoholic. And so that score is very high. Other images can score other ways. Here we have perhaps my favorite meme of all time, Grandma discovers the internet. Grandma discovers the internet. Grandma's clearly very elderly, and so there's a high score there. So the model sees an elderly person in the image and scores that particular column high. And there's nothing in the image to suggest that grandma is alcoholic, although if you've had her pie, you might think she is. It's fortified, shall we say. And so that score is very low. And so this is all an embedding is series of rankings of features of how much a feature that is defined by the model scores. And the important thing is these come out consistently. And so similar numbers map to similar things. So we can take these 3 memes here, and we can run them through this process where we transform the image, and we go through convolutions, and we run it through a model, and we get an embedding out. We get an array of numbers out. We get a vector out. And these are numbers that represent the things the model have found in that image. We can then take another image and then create an embedding, and then the numbers should be similar if the pictures contain similar things. And so in this particular case, I'd like to think that I'm the most interesting man in the world. Although the demo I run does tend to pick him for me, but they also picked the dad from American Choppers, which was what it did on this stage today when I tested it earlier. So, But the idea here is these numbers are similar. And they're consistently similar. So, but how do we measure how similar these numbers are? Well, because we can think of them as a point, and I conveniently used 2 numbers as opposed to 512, we can easily plot these onto a graph. In reality, this would be 512 dimensions, which is a lot harder to put on a PowerPoint. But in this particular case, we got 2, so we can get away with it. And so you can see here in the top right, we've got Leonardo DiCaprio, which is fairly alcoholic. Or in the top center, we have Leo. He's fairly alcoholic, not particularly young or old. Bottom right, you've got grandma on the internet. Bottom left, you've got a couple of kids. My favorite is the top left up here is the drunk British baby. That pint looks so huge next to that baby. I think I like that meme better than I like grandma discovers the internet. But you can think of these as being points in space. And then to see how similar a embedding is simply a matter of geometry. You can do a thing like Euclidean distance. Literally draw a line between the 2 points and measure how long it is. The longer the line, the less similar. The shorter the line, the more similar. Or you can do a thing like cosine similarity. This measures the angle between 2 points. The more narrow the angle, the more similar. The wider the angle, the less similar. These both exist because generic stuff tends to gravitate towards the center. And so you get very general things there. And more specific stuff tends to be pushed out to the edges. And so if I had like a matrix of fast food restaurants, fast food restaurant would be closer to origin than like McDonald's or Burger King or something like that, because they're a little more specific. And so if you care about fast food restaurants, then that cosine similarity, they're going to be in the same line. They're going to be close to the angle. So it'll match things regardless of the magnitude of that vector, regardless how far out they are. Whereas if you use Euclidean distance, you can get some clustering at the end, and things kind of fan out a little bit. And so they both have their uses. I played around, and actually in my demo, I just let you try all of them, but play around with them and see what works best. There's a third one you can use, which is inner product. It doesn't have a convenient geometrical representation, but it tends to split the difference between Euclidean distance and cosine similarity. And so that's often a good choice. I found in practice using inner product on my demo has me show up as Grumpy Cat. I assume it's the hair. Another option is you can do a range query. You can go in and say, I have a point represented by my embedding of an image or text or whatever. Show me everything that's within a certain distance of it. Give me all the neighbors that are nearby. And so these are ways that you can compare these vectors mathematically to do useful things. A vector database then takes these vectors and stores them. And so obviously I work for Redis, so I'm going to use Redis as a vector database for all my examples here. But you can then take all these vectors and associated data and put them in there. So you've got Success Kid, and it's got the image and the title and the embedding for the Success Kid, the most interesting man in the world, mocking SpongeBob. These are all loaded into a database where you could query against them, where you can query against the embedding values using other embeddings, using those techniques. So if you want to find, for example, the closest match to something, you could upload that embedding. You could store a bunch of embeddings in the database. You could upload one of your own as part of your query and find the closest match, or the top 5 closest matches. Obviously, this is a basic function to measure the distance between these points, either using cosine similarity or any of these. It's not super complicated math, but this could be slow. You can't take every point in your database and compare it to every point in your database. You're not going to get a scalability that way. And so an index is essential. Redis and others as well. I don't know all of them, but I know several of the other vector databases. I should say other databases that have add vector features, because Redis is a database that has added a vector feature, where something like Pinecone or Weaviate is a vector database for that specific purpose. But regardless We have two indices that you can create. There's the flat index and the HNSW, which stands for Hierarchical Navigable Small World, which is hard to say on stage. Flat is a simple brute force index. It just tears through the data and finds the best match. It runs into scalability issues after a while. In Redis, if you get about 1 million vectors, you start running into performance issues. So that's sort of the order of magnitude feel you want to see if you want to switch to HNSW or not. Hierarchical Navigable Small World is an approximate accuracy. It gives you less accuracy but better performance, and is tunable for how much accuracy and speed and space you want it to take. So you can make it really big and fast, or you can make it, make it less accurate and slow, and you can tune all the levers. So applications for vector databases. You've got semantic search. This is the simplest use case. This consists of, I've got Redis full of embeddings, and in this case I'm showing text embeddings. Deletion is 100% file compression. TypeScript is just JavaScript for C# devs, changed my mind. And code doesn't compile, compiles again. So we've got these memes in Redis, or in Redis in the vector database, and we've got the embeddings of them in there as well. And then we want to search on something that is semantically similar. Don't need to debug your code if it doesn't compile. So we use a model, turn that into embedding, and then we use cosine similarity or one of those other mechanisms to find the best match. So that's semantic search. It searches on things by meaning. Semantic caching is an interesting use case that's particularly suitable for Redis. Semantic caching is the idea that LLMs are expensive. And if you could cache the questions people ask, cache the results of particular questions from users, you can save some money and some performance. So we've got Grandma here discovering the internet again, and she wants to understand what a dank meme is. The dankest of the dank. And so she's going to ask an LLM. But we also have people have asked other questions about the dankness of memes and dankness and memes and that sort of stuff. And so there's a question out there, what is dankness? And the response from the LLM when it was asked, and an embedding of the question. And I don't understand what memes are with an embedding of that question and then the response from the LLM. And so what Grandma can do is she can create an embedding of her question, hit the vector database, and if you get something that's similar enough that it is within a particular radius, then you just return it. You've got a cache hit, you return the result. And you don't have to talk to the LLM, and you get an answer in milliseconds. If you don't get anything that matches, then you go ahead and ask the LLM the question, return the answer to Grandma, and then go ahead and add that to the cache as well, so that when someone comes in and asks another similar question, that they will get the cached answer instead. The example I like to use here is why are my photos blurry and why are my pictures out of focus? This is the same question. They would rank very similar semantically, and so you would get a cache hit. And last but not least is retrieval augmented generation. This one's been probably talked about to death. It was the hot topic last year. But vector databases do enable this. Pardon me. The idea of retrieval augmented generation is that you retrieve additional context to give to the LLM so that it has something to generate. So you're augmenting its generation with things that you retrieved. Now you can do this using very mundane things, or you can use like a vector query to do this. The vector example is Grandma is again asking about dank memes. But the LLM she's talking to has not been trained on the internet, apparently, and it doesn't know anything about memes, doesn't understand dankness. It just doesn't, it can't answer the questions. And so what you do is you populate a database with information about dank memes. And you make embeddings of that information about memes. And then we ask the question, we create the embedding, we go out to the database and retrieve context about dankness and memes, hand that to the LLM. along with the question, and then return the result to grandma. Now, this doesn't have to be using vector databases. You could, if you had like a bunch of customer data, you could just say, you could go out and just literally retrieve the customer ID and pass in the information that you selected from a relational database. It doesn't, strictly speaking, require vectors, but this is a convenient way if you've got, well, the previous talk is a great example of it, actually, for those who were here in the previous session. You've got, say, like a bunch of legal documents or a bunch of information on a particular topic that the LM wouldn't know that's specific to your company. So that's a super quick intro overview of what are vector databases and how to use them. I do have a demo, but I have a distraction first. And this is that sort of, I want to talk about a way that you can create your own embeddings. The goal here is to talk about, I'm going to talk about convolutional neural networks. And the goal here is to show that it's knowable. And to see that these models aren't just magical black boxes that just do things, that there is a thing inside of them that you can understand. I have this book that I bought when my kids were young. They're all adults now. It's called 50 Dangerous Things You Should Let Your Kids Do. If you're a young parent, I recommend it very much. It's got things in there like play with fire, and use a pocket knife, and climb a tree, and sit on the roof of your house, and things like that. Fun stuff. Well, I have boys, so maybe that's part of it too. But one of the things that was in there that really struck me was you should let your kids take things apart. And if your kids take a thing apart, like if they take apart, say, a dishwasher, they're not, or an old DVD player or something, they're not going to understand everything about the DVD player by taking it apart, but they're going to pull it apart and they're going to see something in there that they can understand how it works. And by and that communicates to the kid that it's knowable. It's like, I don't understand how all this works, but I figured out that part, and so I could probably figure out the rest if I needed to or wanted to. And so I'm going to explain how CNNs work, not so that you can go out and build one, although if you want to, I have a talk about that, but so that you can see that they're knowable and get an idea of some of the principles behind this. So, and also because if I didn't have this in here, my talk would be too short. So, you've probably seen a picture like this before. This is your basic neural network. It's got an input layer where you send in a bunch of numbers. Those numbers are passed into hidden layers to each node in that layer. Math is applied to them, and then at the very end, you get numbers out. And so ultimately, you can think of this as just a function. 4 numbers come in, 3 numbers come out. This is your basic neural network. And then you train this by using backpropagation to adjust the values of the weights and everything inside of the, on all the connections between the neurons, and then that's when the magic happens. Your basic neuron is also a function. And this is the simplest possible neuron ever. You've got an input and an output. This is a totally unrealistic neuron because it only has one input. However, it does also have only one output, which is very realistic. And so what this does is it draws a line on a graph. Given x, give me a y. Go through all the values for x, you could plot them out on a chart. Inside of the neuron is a weight. This weight is multiplied by the input. A bias is associated with the neuron, and that is added to that multiplication, and then you get an output. So your formula is the input times the weight plus a bias, giving you an output. Now, if you're astute or you've seen this show before, you might recognize this formula as being y equals mx plus b, where y is the output, m is the slope as opposed to the weight, and the bias is the y-intercept. And so every neuron is effectively drawing straight lines at its simplest. And that's actually a problem for neural networks, because if you take a straight line, if you take a function that draws a straight line, and you hand it to another function that draws a straight line, and you hand it to another function that draws a straight line, the only output you're ever going to get from your neural network is a straight line. But a straight line is not how most problems work. Most of the problems we want to solve using neural networks have more complicated curvy lines. And so to address this, very smart people added an activation function. And this activation function was applied to the output before it was, well, output. And this will allow you to do other things. And so they played around with a lot of options. A sigmoid would let you take the value and have it approach 0 or approach 1. And now you've got a curve instead of a straight line, and when this feeds into the next layer, now you're getting curvy lines instead of straight lines. Some tried hyperbolic tangent, which is basically a tall sigmoid. What everyone sort of settled on, and what you almost always use now, is ReLU, which I think is perhaps the most, we took rectified linear units and abbreviated to ReLU, when really this is max x0. This is just take, if it's greater than 0, it's the number, otherwise it's 0. And this tends to work the best. It's what's most commonly used. So a more realistic neuron then takes multiple values. This one takes 3, still not terribly realistic, but more realistic. The math is fundamentally the same. It's the sum of the inputs times the weights plus the bias, and that will give you y. So this is like 5-minute intro to neural networks if you've not touched them or gotten into them before. A convolutional neural network is a specialized variation of a neural network that's partially connected. And in a convolutional neural network, it's specifically designed for image processing. And so you've got an input, which I have here represented as a little 5x5 grid. In practice, in the models that we would be using here, it would be like maybe 224 pixels by 224 pixels by 3 pixels, because you'd have a red, a green, and a blue channel. But you input this information, and this is it's just a representation of the actual bits in the image, the actual pixels in the image. You run these through a series of filters. These filters find particular patterns, perhaps a line going from the left to the right, or from top left to bottom right, or a line going straight across, or a line going straight up and down. And then it pans and scans across the image, finding matches to that pattern, and then marks them in the output when it gets a match. And so you end up with a map of everywhere that shape shows up in the image. And you do this for lots of different shapes, and you get maps of all these different shapes. And then these outputs can be fed into another filtering layer, which then says, well, when I have a line that goes up like this, and a line that goes up like this, and a line that goes like this, then that's a pattern that gets mapped out as well. And so then you've got something that finds all the triangles and all the circles. And then you do another layer of hierarchy, and you repeat this, and you go from lines and circles to triangles to faces and cars and images. And these are the convolutions that are decomposing the hierarchy of the image. You can run these through pooling layers as well. The pooling layers serve to sort of compress that data down a little bit. If you have a line that's straight up and down, you got another one that's got a little jog in it, but it's really just an artifact of how it was drawn, then pooling can kind of average that out. It's kind of like squinting. And then when you're finally done with all of it, you can flatten the output. You can take all of the values from the pooling and the outputs and whatever, and you basically get individual neurons that say, well, this output here shows me where there's a cat, perhaps in the top left or the bottom right, or there's a ball of yarn in the bottom left or the top right. And you get a series of features that have numeric values. Now, if you're training this, you of course need another layer on top of this, which is the classification layer. And then that's how you train it, because you would score it against how accurately predicted the image is. But you can rip that final classification layer off of a convolutional neural network, and you have just the features that are fed into that classification. These features are an array of numbers. These features are an embedding. Now, most people are doing this as transformers now, but at the end of the day, you're still getting that array of numbers, those embeddings out. I've got a little bit of graphic here to explain filters a little bit better. So on the left right here, I have I have an image. That's the troll face in pixel art. And then you've got a series of filters that would go across this. And what I really like is that on the right, the top right image here, it matched the eyes perfectly. This wasn't intentional, it just kind of came out this way when I was building the slides. And so the output is showing a map of where like 2 pixels are blocked. And then it shows you where the eyes are at, which I just thought was kind of fun. The way the convolutions work is you're going over panning and scanning. And so looks at there, goes over, and it's looking for matches to that filter as it's moving along. We're not finding a match yet, no matches yet, but it's mapping that filter to the output. There's a map right there, it hit. That didn't hit, that didn't hit. That's a hit, and no hits. And then it pans and scans to the rest of it. And so it creates an output map of that particular filter, that particular shape. But these aren't really pixels. They're not ones and zeros. Or they're not blocks and empty spaces. They're numbers. Now, I've set mine to 0 and 1 here because, frankly, it fits in the little box there. But these would actually be a measure of how red or green or blue or the alpha channel is on that particular image. And the filter is numbers as well, and the output is numbers as well. So you look at this output here, and you see it finds the 2 eyes in the middle, right? Right there. But up top there, turns out part of a line kind of matches an entirety of a line. So it matches not as well, but it still matches. And so you can kind of get a shape of the face there. And these numbers are actually going through that same y equals mx plus b calculation, where x is the value of input, the weight is the filter. So the filter is actually the weights on the connections in the neural network. The bias is there as well. And then the output of all that is run through ReLU to generate the output mapping. And so this is that same process earlier that I was showing you, but it's connected in a different way. So that's convolutional neural networks. Pooling is a similar process. It's fairly straightforward. In this case, we're doing a little 2x2 pooling. And so we'll jump across each section here. And we'll just, if there's something there, then we'll map it out. So in this case, the 2 middle pixels here get mapped, and the rest of them don't. So you're sort of compressing down the image. You can take the max or the min or the average or whatever. And again, these are actually numbers. And so you can see here that these pooling values actually map. And here we're taking the maximum value in that 2x2 area. And so you end up with actually something that kind of very faintly, if you squint, looks like a troll face. It's even got the little chin part jutting out. So after pooling, you would have flattening. And flattening is just taking all those individual values in the pooled output and mapping them to just fanning them out. And these are, again, numbers. So you could use this to build your own embedding models. And you could do it with Keras and Python very, very easily, actually. You're probably tempted to do it. And I would say as a developer, you probably should. I think this would be a fun experiment to just learn and play with these things. This meme is actually terrible life advice. Right? At least that's what my wife said. And but it's terrible life advice, but from a developer point of view, you should totally do this. It's actually good. It's a good learning exercise. However, don't put it in production. We are developers. We are not data scientists. And so we should work with data scientists when we need to create custom models, not try to replace the data scientists with our own work. And data scientists actually need us developers as badly as the developers need the data scientists. Because our specialty is writing code that performs and is maintainable and is scalable and solves a business problem. And data scientists' job is to understand the data and build models that are meaningful, but they don't necessarily build the best code. And so there's a synergy working together with the data scientist to solve these problems. So don't go it alone if you're a developer. Don't go it alone if you're a data scientist. So, but totally try it and play with it. So now I've got a demo where I'm going to use Redis as a vector database. I'm not using a CNN. I'm using models from Hugging Face. I'm going to show you some code, and I'm going to show you a little architectural diagram, and then I'm going to actually do it, and if anyone wants to find out who their meme twin is, then be ready to come down and get on camera. So, and of course I'm going to be using Redis, because that's where I work, but you could totally do this with other vector databases. This is not something unique to Redis. So what I have built is a fairly simple TypeScript application of 3 parts. Well, 4 if we count Redis. We've got Redis. We've got a script called the meme loader. It's a little TypeScript thing that I wrote in Node. The meme loader, when it first loads, connects to Redis and creates an index, telling it that, hey, there's going to be a hash in Redis. It's going to have a title, and it's going to have an embedding, and it's going to have some bytes that represent the image, that are the image bytes itself. Go ahead and index the title and the embedding. It then reads a folder full of memes, and it literally is this is in the GitHub repo. The file name is the title of the meme, and the file itself is a JPEG or a PNG of the meme data itself. And so it creates an embedding of that meme, of that image, and loads that into Redis along with the image itself and the title. So now I have Redis full of images and embeddings and titles. I've got a little JavaScript client. I'm not going to show the JavaScript client off because it's not that interesting. It's a bunch of vanilla JS code that I used, that I struggled to get to work with my webcam. For the most part, it works pretty well, but that was the hardest part, was getting the webcam to work. And I've got a meme server, which is where all the actual work happens. And so the meme client lets you take a picture, and then it uploads that picture to the server. The server takes that picture, creates an embedding, searches Redis for that embedding to find the closest match, gets an ID, fetches that image and the title of that image, and returns it to Redis, and it's returns it to the client, and it's put on the screen. So this is the big fancy application I've written. This is a basic application of semantic search. So let's go ahead and take a look at it and see that it's real. So let me go ahead and get out of presentation mode and wait for things to swap out. I'm going to show a little bit of code first. So I've got this running already. Hey, the camera's working, excellent. So and so this is the little loader code that runs. So you can see all the memes here. There's a good guy Greg, and Grandma finds the internet, and creepy condescending Wonka. No one's ever got the right hat, so that one never matches. But there are a lot of popular ones are in there. This is the code in TypeScript that creates the embedding. It's not really that much of it. So we've got a Hugging Face transformer library that we're bringing in. That's from Hugging Face, of course. And I bring in the pipeline function. What the pipeline function does is it builds a pipeline, something to transform that image to make it the right number of pixels, and then scale the numbers in there so they're between 0 and 1, and break out the red, the green, and the blue channels, and feed that all into a model. And so I call the pipeline function right here. I tell it that I want to do image feature extraction. That is, give me an embedding from an image. Give me 512 features that the model knows about. This is the model that I want to use. I'm going to use Zenova because those are the clip VIT models that work with JavaScript and TypeScript. You can actually run this code in a browser as well, which could be very useful because you could put this in the client side. They can create their own embeddings and then hand up the embedding over the wire, which is going to be a lot smaller. And then just a little bit of stuff to make TypeScript happy. I had to tell it it was using floating point 32. So this builds a pipeline and then assigns a function here to this variable. I then create a little embed function, and it takes a image path. This can be a URL. This could be a file path. This could be a data URL with an inline image. The pipeline, the extractor that we've created, doesn't care. It will figure that out and pull the image down. If it's on the internet, pull it off of your hard drive. If it's off your hard drive, we'll pull it out of the data URL if it's in the data URL. And it will basically, in one function, create the embedding. It calls it a tensor. The tensor has several things on it, but the data itself is an array of 512 32-bit floating point numbers that represent all of the features in the image. And so we pull that out, call that the raw data. And because I'm using Node and because I'm using Node Redis, which is the client library for Redis from Node, hence the name, I need to take the buffer of the float32 array, which is a uint byte array, uint8 array, the raw data.buffer, and then I need to feed that into a Node buffer so that I can hand it to Node Redis. And so, but that is then the embedding. I return it, and that's all the code to create the embedding. To actually do something with it, let's take a look here. Look at the Redis client. Yeah, so for the Redis client, this code's a little more involved, but the key thing here is that you can use ft create, and then you give it an index name, and then here we're saying the title, which is a hash and a value in a hash in Redis, a field in a hash in Redis, is of type text, so we can do full text search on it. And the embedding here, a field named embedding, is a vector. We're using the flat algorithm, not the HNSW. That's 32-bit floats. There's 512 of them, and this is our distance metric, cosine similarity or Euclidean distance or whatever. And then when you go to query, actually let's take a look in Redis here really quick. So if I go into Redis Insight here, and so like here's Drake posting. So if I click on it, you can see we've got an embedding, and that is binary data here, which is why it's printing funny. And we got the image, that's a PNG, and then there's the title. So this is what's in Redis in the hash. I go in here and say, treat this as a 32-bit vector. The embedding gets turned into the actual scores. So this is what's being stored in Redis. And then the querying, how am I doing on time? I got 13 minutes. So for the querying here, we'll go into the matcher. And so when we have this index created, we can call ft search. And there's a query language. Where's that here? Right, there it is. Where you create a query. So star means match everything. And then k nearest neighbor is top one, where the embedding is equal to blob. Blob is passed in down here is the embedding. These are the actual bytes. This is the buffer. So I'm not going to go any more code because honestly, it's all on GitHub, and you're not going to remember it anyhow. So, but the point here is to show, again, that it's knowable. It's out there. You can go look at it. So let's go ahead and try the demo out really quick. Which screen? There we go. OK, so just sit here on my webcam. If I do it, I'm going to say I want it to do Euclidean distance as my distance metric. I'm going to take my photo. There I am. Let's see if we can get something different from cosine similarity. I don't think we will, but let's try. Yeah, it's the same. Let's see if holding an object will make it any different. It's hell-bent and determined that I'm a biker. What are you going to do? Let's go to inner product and see what inner product does. I'm Grumpy Cat. So, yeah, that's pretty much demo. I've only got a couple more slides, but can I get a volunteer from the audience? Someone other than me? Anyone want to come on down? Yeah. Want to be immortalized there on camera here? It's more fun if it's interactive. I really need to make this like a web app so you can all hit the website, but then I would have to spend money on compute, and that violates my first principle, which is I shouldn't have to put a credit card down. So come on up.
I'm going to do the DiCaprio.
Okay, you're going to try doing Leonardo DiCaprio. Excellent. Okay. Take photo. Let's go for cosine similarity.
Yes.
Hot damn! Congratulations, man. I love it when a plan comes together. There was no plan. It's just because he's so shockingly good looking. I say that as a married straight man. So, Okay, so yeah, there's the demo. This is literally, to run this, you can clone the repo, and I literally just did a Docker compose up, and that's all you got to do to get it started. It'll download Redis, it will load the memes, it will do everything for you. If you do try to run this, do know that the meme loader takes a couple minutes to download the model, and then it will start loading up all the memes. So wait till it's loaded all the memes before you try and run it, and don't kill it beforehand because then it'll get confused. But yeah, so that's pretty much the talk. I got a couple more slides here, and then I think some of us are going to go to a boat or something. So if you want to check this out, of course, the code is out here on GitHub. So this QR code will take you straight to my GitHub repo. You can totally rely on it. It'll never give you up, nor will it let you down. If you want to learn more about Redis, you can go to redis.io. Got a website, talks about Redis, imagine that. And at university.redis.io is some free classes. The intro to Redis is actually voiced by yours truly. And so if you want to hear my voice some more, then that's a place you can do it. And more importantly, we have a Discord server. If you have any questions, you can get on there and at me, and I will try to answer them. So one last post here. So we did a performance benchmark of Redis versus competitors, and the number on the left is a throughput speed up factor. So it's a multiplication of how much faster it was compared to the bottom performer for these different benchmarks. So in this first one, Redis is over 50 times faster than, I think, what's the bottom one? It looks like MongoDB Atlas. Whereas for another metric benchmark on the right over here, you can see the numbers are a little more modest. But still, 3 times faster is not nothing. So got a blog post talking about it. You can try the benchmark yourselves. I mean, it's a benchmark, so take it accordingly. Try it yourself, poke it if you need to do something like that. And that's pretty much all I've got. So thanks a lot, and have a good evening.